Section 3.5 is rational functions. Remember, rational just means ratio, so it's a function that looks like a fraction. So these kinds of functions have special issues because we never want the denominator to be 0, and so there are some issues that come with having a denominator. So if we let p of x and q of x be polynomials where q of x is not 0, a function f defined by f of x equals p of x over q of x is called a rational function. And the domain of a rational function is a set of all real numbers excluding the real zeros of q of x. So basically it's saying you can't put in the zeros of that denominator function because those will make the denominator 0, and therefore it will not be defined. So just a reminder about the notation we've been using about x approaching different things in a graph. So if you have line x equals c, like in this graph here, and you use this little notation x approaching with a little arrow, c with a little plus sign, that means you're talking about x approaching c from the right side. If you have x with an arrow and you have c with a negative sign, it means that x is approaching c from the left side. And then when you have x approaching infinity, you're just talking about x increasing without bound. And if you're talking about x approaching negative infinity, you're talking about x approaching negative infinity, decreasing without bound. So that's just some notation that I think you all probably already know. So suppose we have a rational function, f of x equals 1 over x. The domain of that function is all x except for 0. And to describe what this function is doing, we could say these statements. As x approaches positive infinity, that is, as x gets bigger and bigger, going that way, y approaches 0. So you can see that the graph is coming down as x goes to the right. The graph is coming down and it is approaching that x-axis. So y is getting tinier and tinier and tinier, closer and closer to 0. That's what's happening to the function over there. As x approaches 0 from the right side, so as x approaches the y-axis, what's happening to the graph? Well, what's happening to y? Y is shooting up. It's going up toward infinity. So that's what the graph is doing as x approaches 0 from the right side. As x approaches 0 from the left side, as x approaches negative infinity, going smaller and smaller, y again is approaching 0. It's approaching that x-axis. As x approaches 0 from the left side, so it's approaching the y-axis from the left side, you can see that the function itself is shooting down to negative infinity. So y is approaching negative infinity like that. So that's kind of how we use that notation to describe what a graph is doing in any given region. Moving on. All right, so here you have a graph of 1 over x squared. It looks very similar to 1 over x, except the two curves are both above the x-axis because x squared is always positive. So as x approaches negative infinity in this graph, so as x approaches negative infinity, it's going that way. What is the graph doing? Well, it's coming down and it is approaching the x-axis. So it's approaching 0. As x approaches 0 from the left, so it's coming this way, what is the graph doing? The graph is shooting up towards infinity. So f is approaching positive infinity. As x approaches 0 from the right side, coming in this way, again, the graph is shooting up toward infinity, so positive infinity. And as x is approaching positive infinity, so going from 0 up, we can see that the graph is coming down towards the x-axis so it is approaching 0. Vertical asymptotes. The line x equals c is a vertical asymptote of a function f if f of x approaches infinity or negative infinity as x approaches c from either side. So consider a rational function f defined by f of x equals p of x over q of x, where p of x and q of x have no common factors. Okay, so this is going to be important in a second. The function has to be in lowest terms for what I'm about to say to be true. So consider a rational function f, p of x over q of x in lowest terms. If c is a real zero of q of x, then x equals c is a vertical asymptote of the graph of f. So a vertical asymptote will only occur if there's a value that x can never be. So if you look at this function right here, 2 over x minus 3, it's in lowest terms. There's no common factors on the top and bottom. The real zero, the zero of the denominator is 3, because 3 minus 3 is going to give you 0. So that means that x equals 3 is the vertical asymptote. So x minus 3 is 0 when x equals 3. So there is that asymptote. As x approaches the asymptote, the graph will shoot up or down to positive or negative infinity. That's what a vertical asymptote is. All right, so here's another one. We want to find out what the asymptotes for this are. All we have to do is factor. So x minus 4 on top, and then on the bottom, we're going to factor this. So we've got 3x and x, and then we have 2 and 1 to get negative 2. So if we put the 2 here and the 1 here, then we're going to have positive 6 minus 1 will give us 5. So we can see that this fraction is in lowest terms. There are no common factors. And so we just need to find the zeros of the denominator. And those will occur when 3x minus 1 is 0, which means 3x is 1 or x is 1/3, or x plus 2 is 0, where x equals negative 2. So our two asymptotes are going to be x equals 1/3 and x equals negative 2. So let me see if I animated that. Oh, look, I animated the whole thing. All right, so there they are. Those are the asymptotes. The vertical asymptotes are going to occur where x equals negative 2 or x equals 1/3. We got 4x squared over x squared plus 4, and we're trying to find the vertical asymptotes. You can see that this function is in lowest terms. There are no common factors, and so you just want to know when is that denominator equal to 0. And the fact is that it doesn't matter what you put in there for x, it will never be 0. So there are no real zeros, and you can see that the graph has no vertical asymptotes. There are no vertical lines that the graph shoots up to infinity or down to negative infinity as x approaches that line. There are none. So when the denominator doesn't have any zeros, you're not going to have any vertical asymptotes. All right, given f of x equals 3x minus 6, for what values is the function undefined? All right, so to understand what's going on here, first of all, we're going to factor the function. So you can see there's a common factor of 3 in the numerator, so 3 times x minus 2. And then on the bottom, you're going to factor that, and it's going to be, so you're going to have a 2 and a 1, so you want a negative 2 and a positive 1 so that you can get a negative x. And you can see that there is a common factor on top and bottom that you could cancel, but then it wouldn't be the same function as it is now. But what that does tell me is that 2, x equals 2, is not going to be an asymptote. Because remember, to find the asymptotes, you have to make sure that the function is in lowest terms. So the function is undefined when x equals 2. So for part A, for what values is the function undefined? It's undefined when x is 2 and when x is negative 1, because either one of those will make the denominator 0. But x equals 2, since it is a factor on top and bottom, that x minus 2 is a factor on top and bottom, that is not an asymptote. That is just an inconsistency in the graph. So if you have a hole in the graph somewhere, a point where there is no um, there is no f of x at that point. That will look like this. It will look like, you've got a normal curve going on and suddenly there's a hole. All right. That means that there is a value of x that the function does not exist for, but that is not an asymptote. And the way you can tell that algebraically is that you will have a factor on the top and the bottom that could be canceled and does not represent an asymptote. So the only asymptote we're going to have here for this one is x equals -1. So you've got that factor on top and bottom, which means that x equals 2. There's no value for the function there, but it is not an asymptote. So for part B, it says write the domain of f in interval notation. So we got to do that. So remember, the domain is just all the values you can put in for x that will make the function have a value. And the only places you're not allowed, the only x's you're not allowed to put in, as we said, are 2 and -1. So the domain is going to go from -infinity up to -1, because we can't include -1, and then union from -1 up to 2, because we can't have 2, and then union 2 to infinity. So that's the domain. Anything but -1 or 2. And then part C, what is the vertical asymptote? And as I said before, we can only look at the function when it's in lowest terms, and that would mean canceling the x minus 2's, and all we're left with as a 0 for the denominator is -1, is x plus 1, and which has a 0 of -1. So that is the only vertical asymptote. And as you can see from the graph, as x gets closer and closer to the asymptote, the graph shoots up to infinity or down to -infinity. So that is the definition of a vertical asymptote. All right, so vertical asymptotes, that's how you find them, and that's all there is to it. And the graph, remember, never touches the asymptote. All right, horizontal asymptotes. So if we look back at the graph of the function f of x equals 1 over x, we can see that the y-axis is a vertical asymptote. We knew that already. We also see that the x-axis is a horizontal asymptote. When we're looking for horizontal asymptote, the line y equals d is a horizontal asymptote of f if f of x approaches d as x approaches infinity or -infinity. So a horizontal asymptote will only occur if there is a value that the function approaches as the absolute value of x approaches infinity. So the horizontal asymptote, I can't say that the function will never have that value, because you'll see that sometimes it can cross the horizontal asymptote. But I can say that the function will always end up approaching the horizontal asymptote as x goes to infinity or -infinity, and you'll see that when we do an example. So there are 3 different situations for finding horizontal asymptotes. So we're going to look at the different kinds of functions where you can find a horizontal asymptote. So this function, f of x equals 8x squared plus 1 over x to the 4th plus 1. First thing you're going to notice, you need to notice for the horizontal asymptote situation, is that in this function, the degree of the numerator is less than the degree of the denominator. So the degree of the numerator is 2, highest power on x. The degree of the denominator is 4, highest power on x is 4. So what does that mean? That means that the denominator is going to dominate this function. Whatever has the highest degree, that is going to just take over as x gets really large. And so if the denominator dominates, the fraction is approaching 0. That means because as the denominator gets really, really big compared to everything else, that fraction is getting tiny, because like 1/1,000,000th is a tiny, tiny fraction. So if the denominator starts getting huge compared to everything else, then the actual function itself is approaching 0. Therefore, the value of the function approaches 0 as the absolute value of x gets very large, and therefore the x-axis is going to be your horizontal asymptote. So, bottom line, if the degree of the denominator is bigger, if the denominator dominates, then your horizontal asymptote will be the x-axis. You can see that in this graph. So here's another situation. G of x equals 2x cubed minus 6x over x squared plus 4. In this function, the degree of the numerator is greater than the degree of the denominator. That is, 3 is greater than 2. So in this one, the numerator is going to dominate the function as x gets very large. So as x gets very large, the numerator is just going to outweigh everything else. And if the numerator dominates, then the fraction is approaching infinity or negative infinity. It's just getting huge without bound. Therefore, G has no horizontal asymptote because it's not going to approach any horizontal line. It's just going to keep getting gigantic, either positive or negative. So no horizontal asymptote when the degree of the numerator is bigger. The numerator dominates, then there's no horizontal asymptote. So that is the second situation. Next situation. In this function, the degree of the numerator equals the degree of the denominator. So 2 and 2. So neither is going to dominate the function as x gets very large. The leading term, 8x squared, will dominate the numerator, and the leading term, 2x squared, will dominate the denominator. So as x gets very large, that numerator is just going to look more and more like 8x squared. As x gets very large, that denominator is just going to look more and more like 2x squared because the 1 and the 9x minus 5, they're just not even going to matter anymore. So h will look more and more like 8x squared over 2x squared, which is 8 over 2, which is 4. So therefore, and I mean by gets very large, I mean either positively or negatively gets very large. Therefore, h has a horizontal asymptote at the line y equals 4. And so you can see in this graph here that even though the graph does cross that horizontal asymptote at a certain spot, it turns right around and comes back toward the asymptote. So the asymptote is still what the graph ultimately approaches. As x gets bigger and bigger, either positively or negatively, the graph starts approaching the asymptote and just keeps on approaching it closer and closer. And we're going to talk about the way you would know if the graph crosses the asymptote. And yeah, we're not doing that here, but we'll do that actually in the next page or next slide. So any question on that so far? Those are 3 different situations that help you know what the horizontal asymptote could be. It can either be the x-axis, it can either not exist at all, or it could be a line like this where it's an actual number like y equals 4, something like that. All right. So a function may not cross a vertical asymptote ever. However, a function may cross a horizontal asymptote, as we saw in part C of the last example. So given h of x equals 8x squared plus 9x minus 5 over 2x squared plus 1, we can determine the point where the graph of h crosses its horizontal asymptote. So we found out that the horizontal asymptote was y equals 4. So all we have to do is see if we can figure out, can the function equal 4? If the function can equal 4, then it will definitely cross it. If it can't equal 4, then it can't touch it. So to figure out if the function can equal 4, all we have to do is set the function equal to 4 and solve for x. So we've got 8x squared plus 9x minus 5 over 2x squared plus 1 equals 4, and we need to solve it. So we just multiply both sides by 2x squared plus 1, and then just multiply all that out and get everything on one side. So I just canceled the 8x squared, and we have 9x minus 5 equals 4, so add 5 to both sides, and you just get 9x equals 9, so x equals 1. So when x equals 1, this function equals 4. So at x equals 1, that's where it crosses. So 1, 4 is on this graph, and that's where that function crosses the horizontal asymptote. So that's all you have to do to figure out if it actually touches it or crosses it. Okay, slant asymptotes. Sometimes the graph of a rational function will have a slant asymptote. This happens if the degree of the numerator is exactly 1 greater than the degree of the denominator. To find an equation of a slant asymptote, you just divide the numerator by the denominator, and y equals the quotient that you get without the remainder will be the equation of the slant asymptote. All right, so let's just look and see what all the asymptotes for this function are. F of x equals 2x squared minus 5x minus 3 over x minus 2. First of all, you can see, first of all, you would want to factor it to see if you have a vertical asymptote. So the top factors to 2x plus 1 times x minus 3, and the bottom is just x minus 2. There is no common factor here, so you know that the only vertical asymptote is going to be the 0 of the denominator, which is 2. So there will be a vertical asymptote at x equals 2, and that looks like that. Next, for a horizontal asymptote, you can see that the degree of the numerator is greater than the degree of the denominator, and that means that there is no horizontal asymptote. For a slant asymptote, remember, you have to find out if the degree of the numerator, you have to find out if the degree of the numerator is just 1 greater than the degree of the denominator, and that's true. The degree of the numerator is 2, and the degree of the denominator is just 1. So that is the situation where you might have a slant asymptote. And to figure that out, you just do the division. You divide x minus 2 into 2x squared minus 5x minus 3. And to do that, you see how many times x goes into 2x squared, and that's going to be 2x. Then you multiply 2x times x and get 2x squared minus 2 times 2x, which is minus 4x. Then you subtract negative 5x minus negative 4x is negative x. Bring down the negative 3. Divide again, x goes into negative x, negative 1 times, and then multiply, negative 1 times x is negative x. Negative 1 times negative 2 is 2. Subtract, negative 3 minus 2 is negative 5. The remainder doesn't matter. You don't have to worry about the remainder. All you do is you just write the linear equation you get, y equals 2x minus 1. So the slant asymptote is y equals 2x minus 1. That's a line that has a y-intercept at negative 1 and a slope of 2, and that's what it looks like. Sometimes you'll have a graph that you can use transformations to graph instead of, finding asymptotes and all that. So here, we already graphed f of x equals 1 over x squared earlier. We already had that graph. Now we have f of x equals 1 over quantity x plus 2, quantity squared, plus 3. And since we know about transformations, we could just use what we know about transformations to graph this without having to go through all the, stuff. So remember that if you add or subtract something to your x, in your function, like here, I'm adding 2 to the x, that will move the graph either left or right. If you add a number to the whole function, that will move the graph up or down, depending on whether that number is positive or negative. So we added 2 to x, that's going to move the graph 2 to the left. We add 3 to the function, that's going to move the graph up 3 spaces. And so the new graph is going to look like this. So if you notice a function that is very familiar, that looks like a function you already know how to graph, you can use transformations to graph it. All right, if a rational function is not a simple transformation of 1 over x or 1 over x squared, how do we graph it? So that's what we're going to look at right now. and it just takes a little, takes a little work, but it's not impossible. So if we wanted to graph x plus 3 over x minus 2, first thing we're going to do is find the intercepts. The y-intercept is what you get when you put 0 in for x. So f of 0 is equal to 3 over negative 2, which is negative 3 halves. So that's the y-intercept, and we can just put that dot right there on the graph. Then we would find the x-intercepts. The x-intercepts happen when the function equals 0. There's only one there's only one x value that will make this function equal to 0, and that is negative 3, because that will make the numerator 0. We can't make the denominator 0. So the only point where this graph has a 0 is at negative 3, and so we'll graph that right there. Now we'll find the vertical asymptotes. We can already see that this function is in lowest terms, and we know that what is going to make the denominator 0 is going to be x equals 2, because x minus 2 equals 0 when x equals 2. So that is a vertical asymptote, and we'll just draw that. Horizontal asymptote, you can see that the degree of the numerator and the degree of the denominator are the same. And therefore, the leading terms, if we just divide the leading terms, we will get the horizontal asymptote. So x over x is 1. So the horizontal asymptote is going to be the line y equals 1. Now we want to know if the graph crosses the horizontal asymptote. And so we would have to set the function equal to 1 to see if the function actually can touch that or cross that horizontal asymptote. Is the function able to have a value of 1? So x plus 3 over x minus 2 equals 1. Oh, sorry, there is no slant asymptote, because in order to have a slant asymptote, the degree of the numerator has to be 1 greater than the degree of the denominator, and that's not happening here, so there is no slant asymptote. All right, so to see if it crosses the horizontal asymptote, we would just say x plus 3 over x minus 2 equals 1, because the asymptote is y equals 1, and then we'll solve for x. So to do that, you would have to set x plus 3 equal to x minus 2, because that's the only way this could equal 1. And when you do that, you get 3 equals negative 2, which is absolutely false. And so the graph is not going to touch or cross that horizontal asymptote, because it can never be equal to 1. The function can't equal 1, so it can't touch it. All right, next thing you want to do, and I don't know, this is not really quite as important to me, but it's still something you can do. It can help you to draw the graph, is to test for symmetry. Remember that if f of negative x is equal to f of x, then you know that the function is symmetric about the y-axis, but that's not true here. If you put in negative x, you do not get the same thing you would get if you put in x to this function, and so it's not symmetric about the y-axis. If you've forgotten about symmetry, you can go back and take a look at that. All right, so now what you have to do is you have to determine the behavior of the graph on each interval that you're dealing with here. And those intervals involve the intercepts and the asymptotes. So one interval here is from negative infinity. Oh, sorry, no symmetry, right? So one interval that you're going to deal with is the interval from negative infinity to negative 3. As you go from negative infinity to negative 3, the function is either above the x-axis or below it, because it doesn't cross it until negative 3. That's a 0. That's where the function will cross the x-axis and become either positive or negative, depending on where it was. So the first interval we're going to check is as x goes from negative infinity up to negative 3. So you're coming up this way, up to this point. We're going to check all the points between negative infinity and negative 3. We only have to check one of them, actually, because that will tell us what all the points are doing. So we can check any point we want to. And so I checked -4 for x. If you put in -4 into the function, so -4 plus 3 over -4 minus 2, you get -1 over -6, which is 1/6. All right. So if you look in the interval from -infinity to -3, try a point, -4, try an x value. I tried -4. The value of the function there is 1/6. That means the curve is positive in that region, in that interval. You're positive. And so what that's telling me is that the function is above the x-axis. And so what can it do? It can't do anything but approach the asymptote. Your function is going to approach the asymptote. It's going to get closer and closer and closer to that asymptote because there's nothing else it can do. It can't cross it, and it can't go below the x-axis because we know all the values are positive up there. So from -infinity up to -3, as x is going on that interval, that's what's happening to the function. It's approaching that asymptote because it can't cross the x-axis until we get to -3, and then it can cross. All right, so our next interval that we need to look at is the interval between -3 and the vertical asymptote. The y-intercept doesn't really matter. It doesn't tell you that the function becomes positive or negative because whatever's happening to the function after x is -3 as you go up to the asymptote, that's going to be the same the whole time. So from -3, sorry, I guess I should just let the thing draw that. That would have been much better. All right, so as you go now, as x goes from -3 up to the vertical asymptote at x equals 2, let's see what the function is doing. We can pick any point we want for x, stick it in there. So I picked -1, and I put that into the function. So -1 plus 3 over -1 minus 2, and that gave me -2/3 right here. So in this interval from -3 to 2, the function has a negative value, -2/3. So I checked one point, but that tells me everything that's going to be happening in that region, because I know if it's negative, it's never going to cross the x-axis to become positive because there are no other zeros. So it's just going to stay negative, and the only way for it to do that is to approach the asymptote. So it's going to go down and it's going to approach that asymptote. So that's what's happening on that interval from -3 up to the asymptote. Now I only have one more region to check, and that is from 2 to infinity. What's happening on the right side of that vertical asymptote? So I'll try a point. I'm going to try 3. I plug in 3 to the function. That's going to be 3 plus 3 over 3 minus 2, which is going to give me 6 over 1, which is 6. So 3, 6, that tells me the function is positive. 6 is positive. So the function has a positive value above 1. It's above the horizontal asymptote, and it is positive. So there's not much that the function can do up there. It's just going to approach the asymptotes. So I had that point 3, 6 right there. And so what the function is going to do is going to approach the asymptotes on either side. There's just no other way to draw it. Because remember, the asymptotes are where the function approaches the asymptote. As x approaches the asymptote on the vertical asymptote, the function shoots up to infinity or down to -infinity. And for a horizontal asymptote, as x gets very large or very small, that function approaches that asymptote. Here we have f of x equals 4x over x squared minus 4. And so we are going to see what we're going to find out, all that information we just found out. So the y-intercept is when x equals 0. Plug in 0 for x and you get 0. So the y-intercept is 0. So the origin, that's where it crosses the y-axis. The x-intercept is where the function itself equals 0. So 4x over x squared minus 4 equals 0 only when x is 0. So again, that intercept is at the origin. The vertical asymptote is going to be where the denominator is equal to 0. The zeros of the denominator in this case, you've got x squared minus 4 equals 0, which means that x is plus or minus 2. So the two asymptotes happen right there at x equals -2 and x equals +2. Next, the horizontal asymptote, the degree of the numerator is less than the degree of the denominator. So the denominator dominates, therefore the function approaches 0. So the asymptote at y equals 0, that is the x-axis, and it crosses it, you can already tell, at 0, 0, because we already found the y-intercept, the x-intercept. So this is what we've got. The slant asymptote, the degree of the numerator is not one more than the denominator, so there is no slant asymptote. And we can check for symmetry. F of negative x equals negative f of x, so it's an odd function, so it is symmetric about the origin. But f of negative x does not equal f of x, so it's not symmetric about the y-axis. I didn't put that, but okay, so let's see what the graph is doing on the intervals we have. So we're going to go from -infinity up to -2. That's going to be one interval that we're going to do. So we can test -3. If we put -3 into this function, we get -12/5. That's negative. So that means that the function is negative as you go from -infinity up to -2. So it stays below the x-axis that whole time, which means that it just approaches the two asymptotes like that. The next interval you're going to want to look at is from -2 up to the 0. That is where the function crosses the x-axis, because you know the function is going to do the same thing the whole time between -2 and 0, but you don't know for sure if it's going to cross that x-axis there and change to another, either from positive to negative or negative to positive. So you have to check that particular interval first. So -2 to 0. I tested x equals -1. If you put x equals -1 into the function, you get -4 over -3, so that's 4/3. That is positive. So that's telling me that from -2 to 0, the function is positive. It is above the x-axis, and so it's going to look like that. It's going to approach that asymptote from the right side as x approaches -2 from the right side. The function is just going to approach infinity because it's positive the whole time and there's nothing else for it to do but approach the asymptote. Now we're going to check from 0 to 2. That's the next little interval we need to check. As x goes from 0 to 2, what is the function doing? So we'll test by putting in x equals 1 because that's in that interval. If you put that in, you get 4 over -3, so -4/3. That means the function is negative on that interval, and the only thing for it to do is to approach the asymptote. And now we need to see what happens on the right side of the vertical asymptote x equals 2. Is the function positive? Is it negative? What is it? So we will look at the interval from 2 to infinity on the x-axis. We'll try a point, 3. We'll try x equals 3 there and see what we get. If you put 3 into the function, you get 12 over 5, and that is positive, which means that the function is just going to be up there in the first quadrant between the two asymptotes, and it's going to be approaching the asymptotes like that. And if you look at this, you can see that it is symmetric about the origin. So that's what you would expect. All right, so let's graph g of x equals 2x squared minus 3x minus 5 over x squared plus 1. So start at the beginning, find the intercepts. The y-intercept is going to be when you put 0 in for x, and you're going to get -5. So the y-intercept is at 0, -5. So we put that on the graph. The x-intercept is when the function itself equals 0, and that's going to happen when the numerator is equal to 0. So all you have to do is solve for the numerator being 0, and to do that you can factor it, and you are going to get 2x minus 5 times x plus 1, and that is going to be 0 when x is 5 halves or when x is -1. So those are your x-intercepts right there. So the vertical asymptote is going to happen when the denominator is 0, and first of all, you can see that the function is in lowest terms. The vertical asymptote is the 0 of the denominator, but the denominator is x squared plus 1, and that never can be 0. So there is no vertical asymptote. To find the horizontal asymptote, you can see that the degree of the numerator is the same as the degree of the denominator. Oops. Okay. So that means that you just divide the leading terms, and that gives you 2. So 2x squared over x squared gives you 2. So y equals 2 is going to be your horizontal asymptote. And you also need to find out if the graph is going to cross that asymptote by seeing if the function can equal 2. So 2x squared minus 3x minus 5 over x squared plus 1, can it equal 2? Figure that out. We would just multiply both sides by x squared plus 1, get everything on one side. You've got 3x equals -7. So x would be -7/3. So that function will cross the horizontal asymptote at that point, -7/3, 2. All right, now we will see if if it has symmetry about the y-axis or the origin. G of -x does not equal g of x, and I didn't do that out, but you can try it. If you put -x in, you don't get the same thing as just g of x, so it's not symmetric about the y-axis. G of -x does not equal the opposite of g of x either, so it's not symmetrical about the origin. So there's no symmetry at all. And then look for the slant asymptote only if the degree of the numerator is 1 more than the degree of the denominator, and it's not, so there is no slant asymptote. And now we need to look at our intervals. So we're looking at the interval from 0 up to, -infinity up to -7/3. -7/3 is where the function crosses that or touches whichever that horizontal asymptote. So we're going to see what's going on from -infinity up to -7/3. We check a point. We can check any x value we want that's in that interval. So if we try -3, plug that into the function, and you get 11/5. So that's telling me that during that time, from -7/3 down to -infinity, the function is above the line y equals 2, because 11/5 is more than 2. So above that horizontal asymptote, that is to the left of -7/3, the function is just going to stay above that asymptote, but it's going to approach the asymptote also. So it's kind of weird. So it's looking like that. That's not great, but it's doing something like that where it's going to eventually just approach that asymptote. Now we're going to check from -7/3 up to -1, where the function has a 0. We can check anything we want that's in that interval. Probably the easiest thing to check is -2. And if you put that into the function, you get 9/5, which is positive. So that's just telling me that the whole time between -7/3 and -1, as x goes from -7/3 to -1, the function stays positive, and that's kind of what you expect. Now we will check from -1 up to 5/2, because that's the next 0 over there. We'll see if the function is positive or negative in that interval. Easiest thing to check here is x equals 0. If you put that in, you get -5. So that tells me that the whole time we go from -1 on the x-axis up to 5/2 on the x-axis, the function stays negative. At some point down there, it turns around. We may not, find exactly where that happens. Remember, this is just a sketch. So somewhere down there, it turns around because it has to in order to come back up and cross the x-axis at 5/2, which we know happens. All right, so we're going to expect that now from 5/2 up to infinity, the function will stay positive and it will approach the asymptote. So if you check a point, you could check 3 for x and see what you get. You do get a positive value. So the function comes up and it approaches the asymptote all the way up to infinity. All right, so we have this function. We're going to find the y-intercepts. That's when you put in 0 for x, you get 4/3. So we'll graph that. 0, 4/3. When you put in the x-intercept is when the function itself equals 0, which only happens when the numerator is 0 because the denominator cannot be 0. So if we solve this by factoring, we're going to have 2x plus 1, x plus 4. So the two zeros are going to be at -1/2 and at -4. So we can graph those. Now the vertical asymptote. We can see that the function is in lowest terms, so the vertical asymptote is going to happen when x plus 3 equals 0, which is at x equals -3. So that's our vertical asymptote. The horizontal asymptote, you can see that the degree of the numerator is greater than the degree of the denominator, which means there is no horizontal asymptote. The slant asymptote, you can see that the numerator is 1 degree greater than the denominator. So if we do that division, we will find the slant asymptote. I'm just going to do that real quick. I'm not even going to go through it. When we get that, we get 2x plus 3. So the line y equals 2x plus 3 is the slant asymptote, and that has a y-intercept of 3 and a slope of 2, and it looks like that. And now we have to see if the function crosses the slant asymptote, because it can do that. So we haven't done that yet. To figure out if the function does cross the slant asymptote, we have to set the function equal to the slant asymptote. So does the function 2x squared plus 9x plus 4 over x plus 3, can it equal 2x plus 3? Can it equal the slant asymptote? So to solve that, we need to multiply both sides by x plus 3, and we'll have 2x squared plus 9x plus 4 equals 2x plus 3 times x plus 3, which gives you 2x squared plus 9x plus 9. I'm just rushing through this. You can cancel the 2x squared, you can cancel the 9x, and you get 4 equals 9, which is not true, so it does not cross the slant asymptote. Now we need to look at our intervals. All right, as you go from -infinity up to -4, which is the first 0, let's see what's happening. So plug in something like -5 or anything you want into the function. And in that case, you get -4.5. So the function is negative as you are coming down from -infinity up to -4. So as we go from -4 to the vertical asymptote at -3, we'll have to check -4.5 or -3.5. If we put that into the function, we get 6. So the function is positive from -4 to -3. So that is going to be approaching that vertical asymptote there, but we won't do that yet. We won't graph it yet. Now we're going to look at what's happening between -3 on the x-axis and the place where we have the next 0. So from -3 to -1/2. I'll just check -2. That is negative. So as we're going from -3 up to -1/2, the function is negative. It is staying below the x-axis. As we go from -1/2 up to infinity, that's our next interval. -1/2 is a 0. We're going up to infinity. We can try 0 for x. That's the easiest thing, but actually it looks like I'm trying 2. So if we put in 2 for our x, we get 6. So that's positive. So from 2 to infinity, the function is positive. Sorry, from -1/2 to infinity, the function is positive. All right, so this is what we have. When we draw the graph, this is all the things that we just checked on. This is what it's going to look like. All right, here's an application of all this stuff we've done in 3.5. A linear model of the cost for a business to manufacture X items is C of X equals MX plus B, where M is the variable cost to produce an individual item and B is the fixed cost. So the average cost per item manufactured is the sum of all costs divided by the total number of items produced. So that is C of X equals, well, C bar of X is equal to C of X over X. So look at the example. A cleaning service cleans homes. For each house call, the cost of the company is approximately $40 for cleaning supplies, gas, and labor. The business also has a fixed monthly cost of $300 from phone service, advertising, and depreciation. So to write the cost function to represent the cost, C of X in dollars for X house calls per month, that's going to be C of X is equal to, you're going to have $40 for your M. So every single time you make a house call, it costs you $40. So $40 times the number of house calls you make, X. And then you've got that fixed cost of $300 a month, no matter what, no matter how many calls you make. That's your B in your linear equation. Then write the average cost function that represents the average cost, bar C of X, in dollars for X house calls per month. So that is going to be C of X divided by X. Then you want to evaluate that average cost if you make 5 house calls, if you make 20 house calls, 30, and 100. So you just plug those in to get those values. So C bar of 5 is 500 over 5, which is 100. C bar of 20, you just plug 20 in there and you get 55. If you plug in 30, you're going to get 1200 plus 300 over 30, which is about 50. And if you plug in 100 for X there, do that out, you're going to get 43. So we have this graph. This is what the graph of 40x plus 300 over x looks like. There's a horizontal asymptote at 40 because the degree of the numerator and denominator are the same. 40x divided by x is just 40, so there's a horizontal asymptote there. The vertical asymptote is just, the vertical asymptote is just 0 because the denominator is 0 when x equals 0. So this is what this function looks like. So the question is, you can make a maximum of 160 calls per month. However, if the number of calls were unlimited, okay, what value would the average cost approach? It approaches 40 because once X gets really, really big, that $300 no more makes any difference. It doesn't really matter anymore. So the average cost approaches 40 per call because it doesn't, like I said, the $300 doesn't matter anymore once you get a ton of house calls. That doesn't even really matter anymore. Really, all you're having to spend is the money on the cleaning supplies for each call. So that's kind of what that is telling you. So section 3.6 is polynomial inequalities. So we've been talking about equalities. Now we're going to talk about inequalities. So let f of x be a polynomial, then an inequality of the form f of x is less than 0, f of x is greater than 0, f of x is less than or equal to 0, or f of x is greater than or equal to 0 is called a polynomial inequality. So a polynomial inequality is nonlinear if f of x is a polynomial of degree greater than 1. So write the solution set for each of these polynomial inequalities. So I'm showing you the graph here of x squared minus 6x plus 5 equals 0. That is a parabola, obviously. And what we're going to do is look at the different intervals to see when this graph is greater than 0, when the value of the graph is greater than 0, and when it's less than 0. It's greater than 0 when the graph is above the x-axis, so when the graph has a value that is positive, and it is less than 0 when you're below the x-axis, when the value of the graph is a negative number. So as you go along the x-axis, you're seeing when is this positive and when is it negative. When is the value of the function positive and when is it negative? So part A says x squared minus 6x plus 5 is greater than 0. What values of x make that a true statement? Well, those are the values of x where the function itself is positive, greater than 0. When does that happen on the x-axis? It happens when x is between negative infinity and 1. So this part here, all those values of x, the function is below the x-axis. Above the x-axis. So whenever x is over here, you're this part of the function, positive. And then over here, as x goes from 5 to infinity, the function is also positive over there. So the function is greater than 0, positive, on these intervals from negative infinity to 1 and 5 to infinity. When part B is the function less than or equal to 0. When is it negative, below the x-axis, or equal to 0 on the x-axis? Well, that happens here, and those values of x go between 1 and 5. So between 1 and 5, including 1 and 5, that is when the function is less than or equal to 0. Now, in this problem, we looked at the graph to see what's happening, but in some problems coming up, we're going to look at the equation, just the equation, to see what's happening to solve the inequality without having to graph it. So, all right, so if I want to solve this quadratic inequality, just pretend you can't see the graph. If I want to solve it without graphing it, this is how we would do it. I have the graph here so that once we do it, you can see why it's true, or you can see from the graph that it is true. So the first thing you have to do when you want to solve a quadratic inequality like this is you have to get everything on one side. And to do that, you will have to, in this case, just subtract 10 and then add 2x to both sides. So I'm going to move everything over to the left side. 3x times x minus 1 minus 10 plus 2x is greater than 0. And then we're going to add up everything on the left side. So we'll have 3x squared minus 3x minus 10 plus 2x is greater than 0. And then we will just combine everything. 3x squared minus x minus 10 is greater than 0. And now we need to factor it. Find the real solutions to the related equation f of x equals 0. So we've got 3x squared minus x minus 10 equals 0. When does it equal 0? So we need to factor it to find that out. And that is going to be, that is going to be 3x plus 5 times x minus 2. And so the zeros of this function will be when x is negative 5/3 and when x is 2. So we found those zeros, so we know we're going to divide the x-axis into intervals defined by the boundary points. So the zeros are going to be the boundary points here. We're going to look at the interval from negative infinity up to negative 5/3. And then we're going to look at the interval from -5/3 up to 2. And then we're going to look at the interval from 2 to infinity. And we're going to see what the sign of the function is, because we want to know when is the function greater than 0, when is it positive. And so to do that, we're going to set up a kind of a chart to deal with these intervals. So we're going to look at the sign of the factors on these intervals. And because the thing is, we can't just, it's easier if we look at the signs of the factors, because 3x plus 5 times x minus 2 is greater than 0 when both factors are positive and when both factors are negative, because negative times negative is also positive. So we're setting up these intervals and we're going to check the values, the signs of the factors, because what we're trying to find out is when is 3x plus 5 times x minus 2 greater than 0. So looking on these intervals, when does that happen? All right, so from -infinity to -5/3, whoop, sorry about that. So from -infinity to -5/3, that is over here. I'm going to try a value of x that's easy. So I'm going to try -3. And if I put -3 in here to 3x plus 5, so 3 times -3 plus 5, that's going to give me a negative number. -9 plus 5 is negative. So negative. If I put -3 into x minus 2, I'm going to get -3 minus 2, which is also negative. So if 3x plus 5 is negative and x minus 2 is negative, that means that 3x plus 5 times x minus 2 is actually positive, because negative times negative is positive. If I look at the interval from -5/3 to 2, I can pick x equals 0. That's easy. So if I put in 0 to 3x plus 5, I get 5, which is positive. If I put 0 into x minus 2, I get -2, which is negative. And therefore, the sign of that product is negative, because positive times negative is negative. If I look at the interval from 2 to infinity, I can choose 3. If I put 3 into the factor 3x plus 5, I get 9 plus 5, which is positive. If I put 3 into the factor x minus 2, I get 3 minus 2, which is positive. And therefore, the function is positive on that interval. So when is this function greater than 0? It's going to be on this interval and this interval. So my solution would be -infinity up to -5/3, union 2 to infinity. Those are the two regions, the two intervals where the function is positive, greater than 0. So that is the solution set. All right, we're pretty much out of time. I'm trying to decide. I think I should go ahead and post a video so that you can finish section 3.6, because 3.7 is pretty easy, and I think we can still get 3.6 done this week and then do 3.7 next week and have the test on the following week, without us having to have another week to, mess around with all this stuff. So I will put up a video for 3.6, and I will also actually put up a video for 3.5 so that you can have that to help you get the homework done for next week. Okay? So does that make sense to everybody? Does everybody understand? Does everybody get it? Okay? Okay. Great. Excellent. All right. Well, I hope to see you in person next week, and I will try to get all that posted as soon as I can. So see you later. See you next week.